Okay. I think this is working. We'll see. Okay. So this is an experiment in doing some live coding on stream, which I've never done before. And I doubt anyone will actually show up to watch, which is fine, but we'll record it for posterity. So what I'm doing today is I am working on a problem in the user-facing API of my programming game, which if you have not seen any of my devlog videos, looks like this. It's a little game where you control these little dudes, and they run bots, AIs. And right now the main goal of the game is competitive. So you've got a little dude, your opponent has a little dude, and you're trying to score points. It's fairly straightforward. The long-term goal of the game is a little more complicated, but that's the basic idea. And the bots are written in WebAssembly, and today I'm going to be working in Rust compiled to WebAssembly. And this is basically just me dogfooding the game to see what's hard and what's not. And one of the things I discovered as I've worked on this project that I wasn't really expecting is that the hardest problem so far, at least, has been inter-agent communication. Little dudes run around on the screen, they have to plan things with each other. And I've deliberately chosen to make the API pretty minimal. This is the API definitions that currently stands in the WIT format, which is used for WebAssembly components. So this is basically like a remote procedure call style definition. And these are the functions that the AIs can call while planning their turn, because the game is turn-based. And they're pretty simple queries. It's just like, what tiles can I currently see? What creatures can I currently see? Give me some information about myself, that kind of stuff. And in particular, there is a communication method that the characters can use, called broadcast. And what this is if the AI calls it, it will send in a bit string, just like a list of 8-bit integers, and that will be visible to any other agent that can see the agent. So if some other AI calls a visible creatures function, they're going to get back one of these creature structs, and on that will be the data that creature has broadcast, if any. So all communication in the game is line of sight. It's all open in the public, so like enemy agents can see the data as well as friendly agents. That's sort of a design decision. I wanted it to be public. Anyway, so the fact that it's just a raw binary data means that the agents have to interpret it. So this is my sort of test AI that I'm using to do stuff. And let's see, where is my main thing? So much commented out code. Where do I do? Oh, right, it's necessary. Okay. Sorry, lost in my own terrible code. Still lost. I need to clean this up so I can actually find stuff. Where's the component? There it is. Okay, so this AI currently works by it sort of runs some internal code to figure out what it should do. So this is called every turn. And then once it's done with that, once it knows what it's going to do for the turn, it's going to like walk around or pick an item up or whatever. It persists a couple of things. So it stores, persists a broadcastable array, what we were just talking about, and also its internal memory, both of which are stored by the game and will be returned to the character on the next turn. And I'm using bin code, which is a compact binary format that's just really easy to use from Rust to do the packing and unpacking serialization. And so that makes that pretty straightforward. But then you have to decide what goes into it, and that is less straightforward. So here is the structure that I expose to other agents, and right now it's got some stuff in it from previous experiments. And today I'm going to actually replace all of this with some new things that I've written, and those are these CRDT style. I think some of them were actually CRDT's data structures. So these are data structures that are designed to be communicating agents where a network of communicating agents where communication is imperfect. So this is designed to converge on the correct value of the data even after like a network partition, right? So that's perfect for this. So if agent sort of is within line of sight of another agent, they can share data, great. If they drift apart and go off to different parts of the level to do different things, and that data changes, becomes, diverges, and then they come back within line of sight, they need to be able to merge that data into a consistent set. And so long as all the agents are periodically within line of sight of each other, we want the data stored amongst all the agents to eventually converge on a given value, and then that value is going to be used to do planning for things. So that's probably not clear at all, but that's fine. I'll just start working on it. And yeah, anyway, so I've written up some primitives that I'm going to use, and they're based on my previous experiments with what's useful. And the idea for this is code that will be available to players of the game through a library that they can just include in their bots. So this is not core game code, but it's like official standard library stuff. Yeah. And so the primitives I currently have are actually that's the most complicated one. So let's come back to that. So this guy, the expiring first right wins register. So this is a stores a single value of arbitrary type that will always hold the the earliest stored value that the agent has seen, if it's updated correctly. And that's the opposite of what these things usually do. Usually they do last right wins, because you want the most recent thing. But in this context, I want to be able to like claim jobs. So like an agent can say like, hey, I'm going to guard the flag. And other agents should respect that, right? And if they see an agent, if they also come into the world and say, hey, I'm going to guard the flag, and they see someone else who has claimed that role before them, they should give the role up. So that's what this is trying to support. So this will hold the earliest piece, the earliest written piece of data. Fine. And also the data expires, because this world is very unstable, and the agents can die. If you think about this as a network, like the nodes are very unreliable, they can disappear, and so you don't want to respect this data forever, because it's very likely that the agent that claimed it initially is just going to disappear, and there's really no way to know that, right? Except that you can notice that they haven't updated their claim recently. So that's what this expires is. So agents can periodically update the expiry if they want to maintain the claim. That's the idea. All of these are untested. They're just what I think is going to be useful. And I'm just going to skip over how they really work. So this is a related thing. This is a grow only set. So a grow only set is a set of items that nothing can be removed from. So an agent can add things to it, and they can merge their set with other agent sets when they get a chance, and that will just union them together, and you can never remove anything except via expiry. So that's what's added for this version of the code. That's a little bit different than a normal grow only set, is that things can expire, because again, this world is very unstable. And this one is the same as that, except it's got a limited size, right? So it's configured to hold only 5 items or 10 items, and it will evict newer items when an older item is observed if the set is full. And again, that's to support like the claiming of roles, that kind of thing. So this is like, if you want like 5 agents to be trying to score points, then that you might use this set. You set the size to 5, and then when agents come into the world, they'll like try and add themselves to that set. But if they notice that it's full, their new entry will get evicted, and they can see that, and then choose a different role or something. So those are the primitives that I have. I'm going to do some cleanup on this code first off, because there's just previous experiments here. So this is going to take a second, but and it's probably not super interesting, but we're going to do it anyway. So we're just going to clean up, because all of this stuff is basically the noodling I was doing earlier to sort of understand how this should work. Not sure what I want to do with a level map. Oh, right. I was going to talk about this more complex one. So, because sharing map data between agents is useful, I've got this primitive here, distributed look set, which is specifically designed for sharing maps. And what it is it's a grow only set. It does not expire because it's designed for holding data that's persistent, so like the tiles in the world, which can never change. It is so it's a grow only set that you can add stuff to, but the only thing it can hold is these location objects, which are just an XY value. And the idea is that you would put, when you observe a tile that is traversable, you would just stick it in one of these sets. You could store other things in there too, but that's my initial thought. And this is a little more complicated because agents have no access to global positions. The agents only know they know things that they can currently see relative to their current position. So all orientation has to be relative, right? There's no like global compass or anything, no global like GPS. And so when the agents keep track of the world, they have to track how much they've moved, so they can do like an absolute positioning thing. And this just has tools for managing that, that let it like normalize to the frame of the absolute positioning that this agent is using, and then also merge 2 sets that are normalized to different positioning frames with each other, which is a little bit more complicated than what the other things do, but is useful for sharing spatial data. And so that's why I'm thinking about this level map structure, which I'd previously been using to store data about the world. I may replace that with these location sets, but I will think about that. Let's just do that. I'm just going to delete that code, and I may have to rewrite some of it later, but that's fine. Okay. And I don't care about that. Don't care about that. Okay, and I've got some helper stuff. Can't even remember what was in that commented out code, so guess it doesn't matter. And then I was thinking about state machine stuff, but I don't think I care about any of this anymore, so I'm just going to clean this code up. I may come back to this and do state machines later, but right now I don't want to think about that. Okay. And this was also part of that, and it didn't work very well, so skip that. Okay. Also part of that. Let's get this stripped down to absolutely nothing. Okay. Now we've got some more helper functions. These are probably useful. This one's going to change a lot, so I'll just do that, and that, and that. Yeah, I'm just going to have to basically completely rewrite all of this stuff, so I'm only keeping the ones that don't rely on any persistent data. And this is when the bot first loads in, or if somehow its memory store gets corrupted, then this deserialize will fail because either there's no data there or it's corrupted data, and in that case we want to reinitialize. So that is what we're going to do. We're going to recreate the thing in just like an empty memory object, and then it's useful to know the ID of the level that we started on, because like we might descend into dungeons or something and we need to know that that's happened. So we're going to store that, assuming that this is happening in the overworld, in the main level, which is probably true. Okay, and that stuff is fine. So this again, this calls into my function that just calculates my move for the turn, and this persists, broadcasts my data I want to share with other agents, and then persists my internal memory, so that I can retrieve it on the next turn. Okay. And this is so here's my function that calculates the turn, and it's taking this state stuff, which I'm not actually using anymore, so let's clear that out. Right. I no longer need to serialize it either. Since I'm only that. Okay. Great. And so now what I do is I ask the game, this is a query into the game itself. I ask the game what events have happened that are relevant to me since my last turn. And this will be like, I changed levels, which might be because I used an exit or something, or I moved, which could be because I deliberately chose to move, or because I got pushed somehow. In either case, I need to be able to track that. So the change level is going to be important, but I'm not quite sure what to do with it yet, so we'll just skip that one. And then moved is that's relatively straightforward. So this is where I do my absolute positioning. I just keep track of my current location, which when I initially spawn is 0, and then every time I move, I increment it by the delta. And then now I know my position relative to my starting position, which lets me track things in absolute terms relative to that starting point, which is not necessarily the same for every agent. The agents might start at different locations. Okay. And now we're just going to clean up a bunch of stuff that some of this I'm probably going to have to rewrite, but I just don't want to think about it right now. Yeah, let's clear all that out. And okay, so now I've basically deleted all the code that makes any kind of decision, and for the short term, I'm just going to return nothing. So this is just, the AI will never take an action. It will just stand there silently doing nothing, but maintaining some data that it needs to maintain. And then need to think about how to maintain the level map, which yeah, this is code that's going to change because I'm changing how I'm storing level, but we'll just leave the frame intact. This is also going to change because I'm changing how I'm storing it, but I don't know what I'm going to do yet. So we're just going to go. Let's make it crash for the time being. Okay, more utility. Okay, this is interesting, but not directly relevant, so let's just skip that. And then this is for pathfinding. I'm going to be switching to I've already switched to a shared implementation of the pathfinding. But I've changed the function a little bit, so let's see. Why is this wrong? Oh, right. Yeah, to get some Python bindings working, I was doing a thing that I guess broke that. So let's, oh, how am I going to do this? I don't want to solve that problem right now, so I'm going to skip it. But that means that I need to say this is happening in terms of this other type, which confusingly has the same name. This is super ugly, but I don't know. There is a more graceful way of doing this. I just don't want to think about it right now. And that is how we end up with broken code that sits in the code base for years. That is fine. Okay, and these sets are going to be built in also in terms of this other type. These two types, the one I'm moving away from, the one I'm moving towards, are completely identical. Just one of them does the bindings for the game, and the other one is hard-coded into my client utils library, because I was having trouble making the binding stuff work with the Python bindings for this client utilities library, which I will have to figure out eventually, but right now I don't care. Okay, you need that too. And you also need it. Okay, and then this is going to be awful. Okay. And then we do this conversion here. Okay. Now this is coming out in this slightly strange format, which I'll have to deal with later, but that's fine. Okay. So now this AI should compile, and let's just see if that's true. Nope. Why are you sad? Because there is a module that I'm not using anymore. Let's just nuke that. Okay. So this is just an automated build chain that checks for changes in that code and rebuilds it. And now I need the actual game. Let's run that over here. Okay, so let's get this guy set up to actually run the stuff I'm working on. And we're gonna... Where are you building to? I don't remember. Did I put it here? No. It is... that. I see. Need to make copy and pasting working here. That's pain, and then you don't need that. Okay, so now this should load. No, did I type it wrong? Okay. So much stuff. Come on. Not that one, this one. Oh dear. Why are you not loading? You were there. Building a bad file somehow? That's not what I actually wanted. Got data in you, you look reasonable. Is that broken? What a thing. No. Oh, I'm an idiot. Sorry. That is not it failing to load the AI. That is it reinitializing the memory because it successfully reloaded the AI. Okay, so everything is fine. So now we can see that. Sorry, that was more confusion than it needed to be. Okay, so now if we just print a thing, that'll recompile, and now we can see every turn it's printing to the console. Great. Perfect. Okay, so now is the moment where we actually start thinking about interesting problems. We clean this, pare this down to the point where it does nothing anymore. Okay, so first off, I think I want to bring in this distributed loc set, and because I know that I want the friendly agents and also unfriendly agents actually in this case, but no, right now don't care about that. Friendly agents to share their maps with each other, which makes exploring the world more efficient, potentially, because you can just download the exploration that some other agent has previously done. That means that I actually want to share the map data, I want to store the map data on this broadcast struct, because that's the thing that I'm going to be sending to the other agents. So, and let's just go ahead and import these. Default. You need a default implementation. Fine, that makes sense. That is easy enough to do because a B-tree set already has that. So I'll just pull in that. Also needs debug. Okay. This can also be debug. Great. Okay. So now we are storing. And that means because it's stored on this struct, and that struct is automatically broadcast to other agents, it means all the other agents within line of sight can see this, whatever data is in there. So now we need to put some data into it. And we're going to do that in this, which is a function that gets called every turn. So this is my turn calculation. After we have updated our absolute location data. So we know where we are currently in the current turn relative to our initial starting point. And within that context, we're now going to update our map. And so what we do is we ask the game what tiles are visible, and that gives us a list of locations relative to the agent's current location and data about the tile that's located there. And so the first thing we do is we move that relative location into absolute space by just adding it to our absolute positioning data. So now we have the location in absolute space, and we are, for the moment, we're just not going to worry about this. That's going to be important once we start talking about exploration. But for the time being, let us just store the location in the set. And we're going to have to do that same type conversion. That's fine. So the same one we were doing earlier. And just in